Yeah, so as I said, we will continue our journey into dynamical systems. However, we will leave the non-smooth world to go back to the smooth world, which is much nicer. And you will see that actually I will have a different point of view, so I will not focus on understanding neural networks structure as a dynamical system, but rather understanding algorithms as dynamical systems. So this work is based on a collaboration with my wonderful previous collaborators in Paris, Pascal Bianchi, Walid Hachem, and Charlotte Stetman. Okay, so here's the outline of my talk. So I will first explain what we mean by avoidance of traps. So what is this general problem that we're interested in here? And give a general, actually, avoidance of traps result that I will explain. Then we will be able to apply, actually, this result to a very famous, actually, algorithm called the Adam algorithm, which is used in training neural networks and which is very famous. And actually, we will focus on even a class of algorithms using momentum, which are actually popular in practice. And finally, I will just say a few words on an ongoing work focusing on equilibrium learning in games, which is beyond the optimization setting, where now you have several decision makers. And of course, the dynamics becomes much more complicated, and you can see periodic orbits and all sorts of very complicated stuff that Professor Chris Budd mentioned before. And then I will, briefly give some future work and future directions. So let's start with some motivation and with the problem formulation here. So the standard problem that everybody is interested in machine learning is minimizing some function f of x, which writes as an expectation of some function small f of x and c. So you can think of x here as the weights of your neural network or the parameters of your favorite machine learning model, let's say. And this c represents the data and the noise, so each c is a data point actually, and f of xc is just the loss function evaluated at a given data point. So this is a very standard problem. So we will focus on the setting where f is non-convex and differentiable so that we have access to gradients and we can use gradient information to do, for example, backpropagation. And the assumption on the data xn is that it comes from a given distribution which is unknown, but we have IID copies of a random variable whose distribution is unknown, and these are revealed online through the process. Okay, so what can we expect from an algorithm, or what kind of asymptotic, at least, result can we expect when we run an algorithm to solve the problem I just mentioned before? So the typical result for a sequence which is generated by a stochastic algorithm, think about stochastic gradient descent, which is the simplest one, is an asymptotic result of this kind. So with probability 1, we can show that the distance between the iterates xn of your algorithm and the set of critical points is 0 when n goes to plus infinity. So n here is the number of iterations and not the number of layers of your neural network. So really it's like we are running an algorithm for n iterations, and we look at the behavior when n goes to plus infinity. So the question we are asking here, and the main focus of this talk, is this result satisfying? So the answer is obviously no. Why? Because you might end up in some undesirable points, and some of them are saddle points or local maxima, especially if you want to maximize minimize your objective, as we've seen before. So the question I will be focusing on is the following. Do the iterates converge towards these undesirable points? For example, saddle points or local minima or maxima. And we call this, and some people have called this before in the literature, avoidance of traps. Sometimes people call it saddle point escaping or this kind of terminology. So the main viewpoint we will be using here to solve or tackle that problem is the following. That dates back to the 1970s, and it's called the ODE method in stochastic approximation. So this mixes somehow dynamical systems with stochastic approximation because we are dealing with a problem with an algorithm where we have some noise here. So there are several people who worked on this, developing this framework. So back to Lyon, Kushner and Yin, Marie Duflo, Michel Benaim, Vivek Borkar has also a very nice monograph about stochastic approximation, exploiting this connection between algorithms and dynamical systems. And of course, many others. So we are focusing on this algorithm here, with the sequence Zn, which is a sequence of vectors in RD, and we look at this specific update rule, which is actually very general. It has, this H here depends on n, the iterate number, Zn, the previous iterate, and Xi n plus 1, which is the noise at time n plus 1. Notice that here we can have an explicit dependence on n, so the system can be non-autonomous, and actually it can be a gradient, it can be anything. So this framework is very general. Usually it was initially used to solve, to find zeros of a given operator, right? So it can be a gradient or something else. So the idea is to introduce the expectation of that vector field with respect to the past of the observations. So this gives you a mean field, right? A vector field of an ODE, and then you have some additional noise, which is a martingale difference sequence here, eta n plus 1, which needs to be controlled, of course. And here is the ODE that you obtain, z dot equals h of t and z, and as I mentioned, it can be non-autonomous. In the case of the gradient flow, of course, it is autonomous, so it is the simple case, but we will see that in a presentation it will be important that this can be non-autonomous. So now I will straight away give you the result, the general avoidance of traps. So it's a big theorem. I've removed all the technical part from it. It's still technical, but we will try to skim through it and I will walk you through the general result and what it means. So we start from the general form of the algorithm I mentioned before. So this is the sequence Zn we are interested in. Think of the weights of your neural networks which are trained through the optimization process. Then we'll actually use ideas that are very classical in dynamical systems. But now with the stochastic approximation part, you need to deal with that noise and see how you can actually show something using that. So the idea is simple, is that around some z star, you will suppose that you have a linearization around that. So this is very classical in dynamical systems. So this is the vector field h of tz, which writes as a linear part plus a perturbation. But now the perturbation is non-autonomous because it depends specifically on the time t. And this decomposition is useful, of course, around the point z star of interest. Of course, what we will be using afterwards is a critical point z star. And we want to understand the behavior around this critical point. But here I'm giving the theorem in its general form. So now you will look at this matrix D and decompose it using these Jordan blocks. And what is very important is to distinguish between the eigenvalues that are positive and the ones that are non-positive. Precisely to study this stability behavior of the algorithm, which is also very classical in control, for example. Although there is no control here, or even dynamical systems. So now we will make assumptions on the different parts of the algorithm I mentioned at the very beginning. So there is a bias term, Bn plus 1. Of course, we will need the bias to be very small, and actually we need this square integrability condition for the bias. Think about the bias induced by your estimator of the gradient, of the true gradient. Then we need an assumption on the perturbation that I mentioned, E of t and z. So we assume that it's regular, that it is sufficiently smooth. I'm not detailing the exact assumption here, but basically it is 0 at z star, and the important part is that it should vanish in some point to be controllable. So this is the assumption we make here, that the first derivative with respect to z goes to 0 when z is closer to z star, and when t goes to plus infinity. So this assumption will be satisfied actually when we will apply it to the specific algorithms we are looking at. And about the noise, again, as I mentioned, it's a martingale difference sequence, so the expectation with respect to the past is 0. But the crucial assumption, and really I insist on this is the most important part of it, of this theorem, is that the noise projected on the space corresponding to the positive eigenvalues should be sufficiently exciting. So that's the key point to have this escaping phenomenon and avoidance of traps. So this is really key. And we don't need the noise to be exciting in all the directions, just exciting in the direction when we have this instability, which induces the instability. That's the only requirement we need. Under these assumptions, we can show that actually Zn will never be stacked in Z star. So with probability 1, Zn will not converge to Z star. That's the result. Okay, that's the general result. I think we have looked at now the general statement. Let's look at an example. And what is the approach that we adopt to show this result. So, of course, we rely on some, this question has been investigated before by some people. For example, Pimentel in the 1990s, Brandian Duflo, Michel Benaim. So they proposed an approach to do that, but they did not consider non-autonomous systems, so we are extending that to the non-autonomous system part. And I will explain here in a very simple autonomous example, just to give you an idea, intuition about what is going on and how we prove this kind of result. So this is the simple ODE we have. So the form here does not matter a lot, but this is the exact vector field we are considering here. So I'm representing here the flow. As you can see, we have a stable around Z star, which is a critical point, 0, 0. As you may see, it's a critical point there. So this is the stable direction X and stable direction Y in red. And you can see the flow. What we can show is that there is an invariant manifold here. The invariant manifold is in blue here, this M, Y equals X squared. And this invariant manifold is actually the maximal set where the only way to go to Z star equals 0, 0 is to initialize in this manifold. Then the flow would lead you to 0, 0. Otherwise, of course, as you can see in the picture with the flow, you cannot actually end up here if you are not there. So the main idea is to show that actually the noise, if the noise is exciting, and now you might already see the idea here, if it's exciting here, sufficiently exciting in the direction Y, which is unstable, you will stray away from that manifold, and you will not be trapped in the manifold, right? So we are not randomly initializing the first iterate here. We just need that the noise to be sufficiently exciting during the run of the algorithm. That's the key point. Okay, so now we have an idea about how to prove this result. But just to be a bit more technical, I will not go fully into the full proof of the result, but I just want to mention two tools that are important to extend to the non-autonomous setting. So in the dynamical systems literature, this non-autonomous invariant manifold have been shown to exist and well studied by Poche and Rasmussen and some other also people who developed a line of work on that. So we are relying on this particular result from dynamical systems and another result from stochastic approximation. So I will just parse it with you very quickly, but the important part here is that in the proof we will do some change of a variable to come to this result to be used. So basically, imagine you have a sequence like this, n plus 1 with this update rule here. If with Hn, which is a sequence of matrices which converges to a matrix H, but H has only positive eigenvalues, okay? We can show that if the noise is exciting, so this is the positivity here condition, then we will not get retrapped in 0. So I'm using here 0 instead of Z star because we are not centering we are just centering around that point. So we show that actually we will not get trapped in that point. And how to use the previous, so how do we use then invariant manifolds in that story? So the idea is very simple. Well, very simple. The technical details are quite complicated, but the idea is simple. We do a first change of variable. We start from Zn, not this one, but the Zn. We are interested in the algorithm. We do a change of variable to go to in the basis of the stable and unstable directions, right? Which is a natural idea to do. But then what we do is we do a second change of variable by introducing a variable which will be then, so as I mentioned, we start from Zn. We do a first change of variable in the right basis. So we have the stable part and the unstable part. And then the second change of variable is to introduce a new variable u n plus, which is the difference between y n plus minus, and here we introduce the invariant manifold, minus w of yn minus tn. And we keep the second one unchanged. And we will apply the theorem to that second sequence. So basically the idea is that this sequence somehow captures the difference, the distance to the manifold, right? And we will show that actually this sequence precisely will satisfy this theorem, and then we obtain the result this way. Okay, so now we discussed the proof. Let's look at the application. So why are we interested into this? Adam algorithm is very popular. I checked yesterday, it's more than 120,000 citations. So basically anyone who is using a deep learning network usually uses this kind of algorithm. And so we will be discussing here how to apply this technique to the specific case of Adam and also other algorithms actually. So here is a general algorithm which includes Adam somehow as a particular case. It has 3 different sequences. Xn is the main sequence of update. You see that we are updating in a direction which is the opposite direction to some momentum, which is also normalized. So I will not comment a lot about this, but the idea is that there is a kind of adaptive step size which uses past gradient information to update, to have an adaptive step size. And instead of following the opposite direction of the gradient, we are filtering the gradient by using a moving average. So that's the simple way to explain it. And here in this algorithm, as you see, if you choose the different sequences I introduced here, Pn, Qn, Rn, and Hn in some way, we recover several algorithms. SGD with momentum, Adam, Adagrad, RMS prop, which are also very famous, and some other algorithm like stochastic Nesterov accelerated gradient. So for this class of algorithms, we can apply our framework. We come up with a non-autonomous ODE for that, which actually explains the behavior of those algorithms. As you may see here, it's quite similar to the previous system of equations, which was discrete. So we have this system here, and we will be actually, the first result we have, I will not comment a lot about this, but that was the first natural result we would expect. So we proved that actually it is the case, that Xn will go to the set of critical points. So this is the expected result. It's not easy to prove because you need to find the right Lyapunov function. So of course, this is always the key argument here. So we designed this Lyapunov function, which has the first term, which is the potential, the second term, which is the kinetic energy. But now the kinetic energy is also non-autonomous and is also rescaled by some v here because we have the rescaling in the algorithm by some sequence v, right? So it's more complicated and not as standard as SGD, for example, where you would just have this term, f, which is always the potential, right? Okay, so once we have this nice result, as I mentioned, now we are interested in the avoidance of traps result. So how can you apply the general theorem I mentioned before to that particular class of algorithms? Okay, so let x star be in the zeros of gradient f. So x star basically is the critical point we are converging to. Let's suppose we have an unstable equilibrium, meaning that this x star is unstable in the sense that the Hessian of f has actually a negative eigenvalue. So we want to escape basically that point. We don't want to be trapped there. And as I mentioned before, the key assumption is the exciting noise. So we want the noise to be, the variance of that noise to be non-zero. The covariance of the noise to be non-zero, of the stochastic gradient. So that's an assumption, but of course you can also inject noise to guarantee that this assumption is satisfied. So once you have this, then yeah, you just apply the theorem and you get that the n will not be trapped in Z star. That's the result. So I will briefly comment now on the case where we have several decision makers instead of just one. Of course, it's a much more complex setting. This is ongoing work, but I would like to give you an idea about how we would proceed in that case and what can we show also similarly. Because this framework that I mentioned at the beginning, this general result can also be useful in games, not only for optimization. So this is the standard setting we are considering here. We have the game setting is n, is the set of players. So we have capital N number of players interacting between each other. AI is the set of different actions that each for player I, so can choose several actions. In the control theoretic somehow vocabulary, it will be the controls, right? But you were talking about actions in game theory. And you have UI, the utility of each player. So each player has its own utility, UI, depending on the joint strategy. So what is important here is that, of course, the strategy, the utility depends on the behavior of all the agents and not just their own behavior. That's the critical part. So all this is standard. We define the concept of Nash equilibrium because each agent is maximizing their own utility, but actually the interesting concept to look at is in game theory is Nash equilibrium. So we suppose that for each I and for each strategy for player I, unilateral deviation of player I's strategy cannot improve over that point x bar. So that's what we call a Nash equilibrium, right? And this is just explained here in this equation. So now it is known in the computer science literature that actually this problem, computing a Nash equilibrium is very hard. And so we need to look at special classes of games for which we can say something. So let's focus here on a particular class of games, which is called the potential games. This has a wide applicability. It's used in traffic networks, flows, congestion problems. So, and this says the following thing. Basically, the deviations of the utility here, when the strategies of other players are fixed, are captured by a potential function phi. So the important thing here is that phi does not depend on the player. So actually, it's as if they're optimizing this potential function, but of course they don't know it. So that's the crucial point, crucial property here of potential games. And so the question here is that in the game setting, we have several Nash equilibria. So the question we ask is, can we avoid some undesirable ones here? And this equilibrium selection problem is actually a very long historical problem that is very well known. There is a lot of literature around it, mechanism design, ways to steer dynamics towards specific Nash equilibria. But I'm just focusing on this particular problem and show how we can leverage this machinery that I described for this particular problem. Okay, so we will focus on a specific algorithm. It's called mirror descent to solve this, to find Nash equilibrium, basically. This is well studied, very well studied. And we consider the case where we have this entropic irregularizer. So what does it mean? Basically, you have a sequence yn, which somehow stacks the different values of the gradients, right, over time, which gives you information about the utility. And then you just map those values of yn into the set of strategies by just using exponential map or logit map. This is also very standard. And you get this algorithm. It has been shown in the literature that this is related to the replicator dynamics, which is also very known dynamics in the literature in dynamical systems. It was proposed by Taylor and Jonker in 1978 in the context of ecology, biological systems. Basically, you have populations of different species, and some of them will survive or get extinct. So, and basically, you can see here that this x dot over x, you can see it as a log, as the derivative of the log of x. And basically, this rate of change of the species, you can think about it, is controlled by the difference between the fitness of some species with respect to the average. So if a species is very fit compared to others, then it will survive, otherwise it will probably get extinct. So that was the initial motivation. It turns out it describes very well that algorithm. So now, how would we prove what we have here? So basically, that's the theorem, ongoing work. Again, if you have x bar, which is a limit point of that algorithm, stochastic mirror descent, you look at the rest points, which is also rest point of the continuous time replicator dynamics. Then, if you suppose that this x bar is either not a Nash equilibrium or unstable under the replicator dynamic, then we can show the expected result under the right assumptions. We will not converge towards that unstable, basically, equilibrium. And the goal is to show that we converge to some strict, for example, Nash equilibrium, and strict Nash equilibria are known to be more robust, right, compared to mixed ones or, yeah. Okay, so let me conclude now. Here is a summary. We presented the general theorem for, which is a non-autonomous avoidance of traps theorem that we discussed, which is very general. We used tools from dynamical systems and stochastic approximation mixed together to show our result. And we applied it to different contexts. One of them was a class of stochastic algorithms, which is actually very popular in machine learning. And the other one is in a context of learning in games. I want to conclude with maybe a few possible directions. How can we quantify maybe the speed of convergence to escape that manifold? It's actually pretty important. There is already some work for the particular case of SGD, for example. But it's not clear, for example, why this momentum would help you escape faster, or why, or can you show very precise results showing that indeed there is a very clear advantage for this class of algorithms? That would be interesting. And can also, actually, there is another interesting direction related to the previous talk of Professor Chris Budd about non-smoothness, non-differentiability. So of course, neural networks, you can expect this kind of non-smoothness, non-differentiability, but unfortunately, the approach would not work at all. You need to come up with something else now. Because you don't have this smoothness, you cannot invoke smooth invariant manifold. So you have to come up with a few techniques. There are very recent works by Temek Davis and collaborators, and also my previous collaborators working on this particular question in the non-smooth setting, using different techniques. And finally, I've learned in this conference about Koopman operator theory. I've almost never heard about it before. Maybe we can leverage that to do something in that particular, instead of using this ODE method, maybe use another point of view using Koopman operator theory. Yeah. Thanks a lot.